So today we look at Dumas theorem. Okay. We write it in a different spelling. It's a French name, right? Named after a mathematician. So Dumois. Okay. So Dumois is a Dumois, right? Very hard to pronounce. So Dumas theorem. What does it state? Okay. So it's somewhat connected to Euler's theorem. You can see the relation very soon. Okay. So what it says is, suppose you have e power n theta. I'm just combining both and giving you a formula. So if I have e power I theta whole power n, right? Whole power n. What is this equal to? Just look at it. We know that e power I theta is nothing but cos theta plus I sin theta, correct? So if I simply write cos theta plus I sin theta whole power n, correct? So according to Dumas theorem, so this cos theta plus I sin theta whole power n gives you cos n theta plus I sin n theta. Now you can see that if I directly give you the formula, you can see how is this magically coming down, because one is an exponential function, one is a trigonometric function, right? We're really not able to see how that is happening. Okay. But if you look at it in a different way, okay, because of Euler's theorem, we know that e power I theta is nothing but this. So what happens here? So let's now try to combine these two theorems, right? So it is e power I theta into n, okay, because it's a power, say, b whole power c, okay, so it will be a power bc. Now, this is nothing but we can see is cos n theta by Euler's theorem, right? So sin n theta. Okay. So you can see the connection now. Okay. So this, if I write in this form, the Euler's form, right? And then again multiply and get back, you're going to get this theorem. It's very important. Okay. So what it says, raising to the power is very easy in complex number. Okay. So when I raise it to the power of n, okay. So what happened? The n came down and it got converted somehow in terms of angle. Okay. But we already knew what we are talking about. See, this quantity, right, in complex number, is usually talked about in terms of angle. Okay. So it would make sense when I multiply or raise it to the power of, say, 10 or 20. I'm just trying to get the angle, right? So we'll take a couple of examples. I think it will be much more clear how the application helps. Okay. Because if you have higher powers and you're sitting and multiplying or using binomial expansion, it's very tedious, right? Lot of terms, etc. But if you convert in terms of angles, you can see it's much easier. That's the reason we try to convert all the complex numbers to polar coordinates. Okay. Now, let us see one of the examples. Okay. If I want to solve this without knowing any of the theorems, okay. So what would I do? Either I would think of binomial expansion or somehow think of simplifying these terms. So this looks like one of the proofs, right? But again, there are different aspects to it. Now, what we are considering is n to be a whole number here when we are doing this. Okay? When n is not a whole number, this theorem doesn't work that direct. Okay, you have to take different cases, but because you're getting different outputs. Okay, so you can prove that by using a different proof. For this, probably you can prove using induction itself. Okay, by induction it's easily gettable, but for n being a rational number like p by q, we'll see that we'll get more solutions, not only one solution. We need not discuss that in detail right now. What we'll consider is directly this theorem. Okay, so n being a whole number will make it much easier. Let's look at this example. How does it convert and what happens? Okay. Now in this example, you can see that we are raising to the power of 200. Okay. So without Dumas theorem, you can think of, say, probably multiplying or using binomial expansion, right? But still, it's a lot of terms, right? Sitting and writing will take a lot of time. Let us try to convert this. This is in the form, say, a plus ib, right? We'll try to convert in e power terms, then we'll see what we are going to get. So what is the term? It's root 3 by 2 plus I by 2. This, just writing in the terms a plus ib, that's all. Okay. Now, if I take the magnitude r, I want to write in e power I theta terms. What is r? R is nothing but square root of 3 by 4 plus 1 by 4, which is nothing but 1. So r is equal to 1. Theta. Theta is tan inverse of y, which is half by root 3 by 2, which is 1 by root 3, which is 30 degrees or pi by 6. It's fine. Can you see what the problem reduces to? This becomes e power I pi by 6. Okay. If you want to write, you can directly could have seen this as nothing but cos 30, which is pi by 6 plus I sine pi by 6. Correct. Directly from that also you could have written, because we already know Dumas theorem. But our usual traditional way of applying the Euler's theorem, right? We are trying to do that. Now, can you guess what the next term would be? Let me write it in the standard form though. So it is minus root 3 by 2. Remember, the negative sign is for the real part. Okay. Plus I by 2. Okay. So you could guess. Now cos is changing, not sine. Okay. Just look at the terms. So if suppose I just want to check here for different values. Suppose my problem was root 3 by 2 minus I by 2. That time directly, because it's a conjugate of this, this is e power I theta. You could have directly said this is equal to e power minus I theta. Okay. Because it's a conjugate, not an issue. Okay. Now it's not the same. Now what you have is a negative here. Okay. So it is a minus sign to the cos term. So let me write, this is some angle sine, somewhat related to this 30 degrees. In some quadrant, cos is negative and sine is positive. Can you think of which quadrant? It will be in the second quadrant. Okay. So you can try to guess the angle. Okay. What it is. So it is nothing but sine of pi minus 30 degrees. So sine 150 degrees. Okay. So pi minus pi by 6, 5 pi by 6. Okay. Here it will be what? Again, it's cos of 5 pi by 6. If you want, you can check. Okay. Fine. Cos of 5 pi by 6 would be root 3 by 2. So this is nothing but e power I 5 pi by 6. Clear? But it doesn't change your answer. I think any answer you have taken would change much, because most of the times you would get some multiple of pi. But let's look at what we are arriving at. Okay. So I have this is e power I pi by 6 whole power 200 plus e power I 5 pi by 6 whole power 1. Now 200, is not a multiple of 3, so there will be a factor remaining. But let me just simplify this as e power I 200 pi by 6 plus e power I 5 into 200 pi by 6. So one of the factors is 2, so this will be 100 and this will be 3. Okay. And here again, this is 1000. We can just remove one of the factors, make it 3. So whole idea is trying to figure out what angle we are finding. Okay. So e power I. Now this pi by, can you see that 99 by 3 is properly divisible? So I can write 99 plus 1 by 3 just to get in terms of pi, because we know what it is in terms of pi. Similarly, for the other one, 99, I can write plus I times, say, 5 into 99 plus 1 by 3. Just to split it, what are we going to get? E power I, 33. 33 pi plus 5 by 3. Plus e power I, 5 times, okay, 33 pi plus 5 by 3. So you can think of 32 pi. See, every 2 pi of a cycle is complete. So that way, if you think this is nothing but I times, say, pi plus pi by 3, that's it. You can do it in whatever way you like. This is easier for me to understand how many rotations are completed, etc. So I always try to simplify that way. Okay. What about the other term? 5 into 33. So it is, let me see. 5 times 33 pi plus pi by 3. Fine. If I multiply, this is 15, again 15, 16, 165 pi plus 5 pi by 3. Now you can see that 164 pi is nothing but completing circles, right? 164 pi, the entire e power term would end. Now, what is remaining? E power I, pi plus 5 by 3. That's it. All you have to do is go back to your sine form and figure out what are these values. Okay, what is cos of 5 plus pi by 3? What is uh, sine of 5 plus 3 pi by 3? All those things. One second. Okay, now all we have to do is go back to our cos theta plus I sine theta form, right? So try to simplify this. Okay, this is not clear. Let me just write it clear. This is 5 and this is 3. So what is this? The first part would be, this is pi plus pi by 3, which is 4 pi by 3. So all you have to do is find what is cos 4 pi by 3 plus I sine 4 pi by 3. Similarly, cos, this is not 5 pi by 3 together. This is actually, so if you see pi plus 5 pi by 3, this is again greater than 2 pi. So it is 8 pi by 3 actually. So I can write this as, say, 2 pi plus 2 pi by 3. Right? So simply instead of doing that, I'll directly write 2 pi by 3 plus I sine 2 pi by 3. Now all of these angles are known. Correct. And directly we can try to simplify. What is cos pi by 3? Cos of pi plus theta. So minus cos theta. All are negative in the third quadrant. So even this would be minus sine pi by 3. Right. What is the pi? This is pi minus pi by 3. Pi minus theta. Negative. Sine is positive. So it will be I times sine pi by 3. So you can see that your imaginary part cancels off. Real part is minus twice cos pi by 3. Cos pi by 3 is nothing but root 3 by 2. So what we are really getting? 2 and 2 cancels. So we're getting minus 2. So you can see that by just converting this, our calculation become much easier and we got our value directly. Otherwise, there would have been a lot of terms which we had to calculate to get our answer. What I say, 1 plus I whole cube plus 1 minus I whole power 6. Okay. Now again, one of the method is multiplication, even though the powers are a little smaller. Okay. Let's try to use Euler's and Dumas theorem to get our standard results. Okay. Now, first thing, if you've noticed, inside the whole cube, okay, the modulus is not 1. So to convert or to make it 1, what I do is multiply and divide by root. This is a standard form whenever you're trying to figure out, because we know that it's r times e power I theta. Okay. So I simply multiply and divide by r, right, to get the result. That's it. So what will happen inside? This is root 2 times e power. This is pi by 4. I pi by 4. This you have done multiple times, so it's very easy to see. What happens in the other side? Again, the magnitude is not 1. So magnitude is actually root 2. So I multiply and divide by root 2 so that the remaining part, the magnitude becomes 1. Okay. So whole power 6. Again, what does it reduce to? This is root 2 e power I minus pi by 4, right? Because tan inverse of the same minus 1. Okay. So whole power 6. Now can you see the problem has reduced to, so root 2 power 3 is nothing but 2 root 2 e power I 3 pi by 4 plus root 2 power 6 is 2 power 3, which is 8 e power minus I pi 6 by 4. So again, you can simplify this. This is 3, this is 2. Now see, look at this. You can directly calculate 3 pi by 4. Cos of 3 pi by 4 minus 1 by root 2. Sin 3 pi by 4 is plus 1 by root 2. the other part, minus 3 pi by 2. Okay. So cos of minus 3 pi by 2 is 0. Sine of minus 3 by 2 is minus 1. So what remains? So if you see that this root 2 will get cancelled, I have minus 2 and plus 2i plus 8i. So this is nothing but minus 2 plus 10i. Okay. Can you see how the problem reduced very quickly? The other method would have been, you know what is whole cube, we have already figured out what this is. And this again multiply more times to get your answer. Okay. Just converting into the Euler's form, and this power gets easily converted back to cos theta plus I sin theta. So XR is given as cos of pi by 3 power r minus I sin pi by 3 power r. So what will X1 be? Okay, so it will be cos of pi by 3 minus I sin pi by 3. X2 cos pi by 9 minus I sin pi by 9. Correct. Now, can you see the relation? If I simply multiply all these terms, I'm not going to get anything. Okay, there's no, it's that too up to infinity. There's no way I'm going to multiply all the terms. Right? So you can see that converting into e power term, that's the only solution you have. And e power magnitude is 1. Whenever magnitude is 1, it's best you convert and write in terms of e power I theta. So this is nothing but e power minus I pi by 3. Okay. Again, this is e power minus I pi by 9. I think you can guess all the terms right now. So we are just trying to find the product of e power minus I pi by 3 into e power minus I pi by 9 into e power minus I pi by 3 cube now, 27, so on. Now it's product of exponent functions, right? So what do we have? It's e power. I'll take minus I common. Even pi I can take common. Right? So first term is 1 by 3. Next term is 1 by 9, which is 1 by 3 square. 1 by 3 cube. So on up to infinity. So an infinite GP. We already know what the sum is. So e power minus pi into I into a by 1 minus r. What is the sum of an infinite GP? It's nothing but first term divided by 1 minus the common ratio. Obviously, the common ratio should be less than 1, or mod of the common ratio should be less than 1. Okay. So what is this equal to? E power minus pi I into 1 by 3 by 2 by 3, nothing but half. Or e power minus I pi by 2. We need not stop here. We can go back to our cos term, cos of minus pi by 2 plus I sine of minus pi by 2. Cos pi by 2 we know is 0. So this is nothing but minus I. Look at the term. The problem looks very much complicated. We are multiplying a lot of terms. But the final answer what we got is it's minus I. Okay. The value of root I and root of minus I. Now looking at the problem, you might simply say root of minus 1 and stop there. And this is nothing but root of minus 1. Yes. But now, as we have learned to write I and other complex numbers in the exponent form, right? Let's try to use that. So what is I exactly? If I write this as 0 plus I, okay, can I convert it to r plus r into e power I theta form? Yes, we can. Because r is nothing but 1. E power I theta. Theta is 1. Theta is nothing but pi by 2. Can you see that directly without even doing this? This is cos of pi by 2 plus I sin pi by 2. Correct. So we're getting e power I pi by 2. So can you see the advantage of writing this like this? This is root of e power I pi by 2. The first term I'm taking care of. Now we know that square root is nothing but half, right? So whole power half. So it will be e power I pi by 4. Simplified very easily. Okay. Second part, again, it's minus I, or the same form if you want me to write cos of pi by 2 minus I cos of sine of pi by 2. One way you can see is the conjugate of this. So directly you can say that it is e power minus pi by 2. Or you can simply take this minus sign inside and write it as cos of minus pi by 2 plus I times sine of minus pi by 2. Anyways, what you are getting is root of e power minus I pi by 2 or e power minus I pi by 2 whole power half. Again, you can see that this got reduced to minus I pi by 4. Again, a very simple problem. Now simply expand it back to your trigonometric form, which is cos of pi by 4 plus I sine pi by 4. The next term would be cos pi by 4 because cos of minus theta is cos theta itself minus I sine pi by 4. Can you see these two terms cancel? 2 cos pi by 4, which is 2 times 1 by root 2, or it's nothing but root. Okay. So again, one of the better applications of the Moss theorem. Okay. Cos of 1 minus I is equal to a plus ib. So you want to convert this cos term somehow into a complex number. Okay. This is a bit difficult because first of all, you may not know how to write cos terms in terms of complex numbers, right? So first, we'll try to think, if this is the cos theta, how do I get using Euler's theorem? Okay, look at this. Suppose I have e power I theta. It is cos theta plus I sin theta. Agreed? If I have e power minus I theta, I will have cos theta minus I sin theta. Because cos of minus theta is theta. If I add these two, can you see that cos theta is nothing but e power minus theta by 2. Correct? Or nothing but your real part. Okay, you already know what the real part is. Okay, the real part is sum of these two complex numbers divided by 2. Okay, because these are conjugates. Okay. Why am I telling this? We can simply apply the same here, cos of 1 minus I. Okay, because see, even if this is in the form a plus b, there's a cos outside. You can't simply say that this is equal to 1 minus I, right? So the cos function is outside. So somehow we have to try to simplify. So this is e power I into 1 minus I plus e power minus I into 1 minus I divided by 2. Fine. What is it? E power I minus I square, which is plus 1. So minus into minus 1 is plus 1 plus e power minus I into minus 1. Okay. So this will be 2. Now, we know what is e power I. Okay, we don't know what is e power I plus 1. So what will we do? We will write this as e into e power I plus e power minus I minus 1 is nothing but divided by e. Divided by 2. If you want to write it in a better way, okay, so let us start writing what is e power I. See, we know e power I theta. Whenever this is I theta, we write it as cos theta plus sin theta. Now, there is no theta. No theta means what? Theta is equal to 1. So if I have e power I, it's nothing but cos 1, radians we are talking about. So plus I sin 1. Same thing I'll substitute here. It's cos 1 plus I sin 1. Right. For the other part, we have e power minus, this is 1 by e, which is a constant outside. Same logic. Okay. Cos of minus 1, which is cos 1 itself, minus I sin 1. Fine. Now, all that remains is simplification. I'll just combine the real part and the imaginary part. Real part is this term and this term. So it is cos 1 into e plus 1 by e. And there's a 1 by 2 here. Okay, just operating it. Plus, same logic here. There is half into sine 1 into e minus 1 by e. Again, we have I here. So I terms are 2. So what do you want? A, this is nothing but A now. And the remaining part is B. Clear? So the whole trick is you should be able to figure out what A cos theta is in terms of E powers. Okay. Because there's no direct method to just convert cos. Okay. If you do a simple angle, we know. Okay, sine theta might have been 0. Okay, but there's a complex number inside. Okay, there's no easy way to get rid of that. This is the method you have to follow. Okay, now we'll talk about cube roots of unity. Okay, and we all have seen this equation before. So x square equal to 1. Whenever we have x square equal to 1, we say the solutions of this equation are x is equal to plus or minus 1. And x square equal to minus 1, we just thought about it. And we started off the entire chapter, say complex numbers, right? Based on, because we didn't know the value, we consider this as I and got to complex numbers. Now, can you tell me what happens when I do x cube equal to 1? Okay. One of the solution we all know, that is x equal to 1. Okay. And now because it's a polynomial, okay, and degree is 3, we all know that the degree gives you the number of roots. Okay. So in this equation, it says x cube is equal to 1. So it's a third degree equation. So totally it should have 3 roots, right? So we got only one root, which is 1. By observation, we can say one of the root is 1. So what are the other 2 roots? Okay. So these 3 roots combined are called as cube root of unity. Okay. We'll try to figure out how to get the roots. So usually I think you would see this equation, z cube is equal to 1. Okay. Because that is a complex number. You get an idea right now. So other 2 roots are not real, but complex. Okay. But we already know how to figure out the roots. If it's a cubic equation, this is the equation, z cube minus 1 is equal to 0. How do you solve a cubic equation? If you know one of the roots, we just remove the factor out. Okay, remaining will be a quadratic equation. So which is the root we know? We know that one of the root is 1. So you simply divide, say, z minus 1, you just divide z cube minus 3. So if you divide, what you get? Z square, z cube minus z square. Okay. Subtract. So you'll get z square minus 1. Okay. Again, plus z you do. You'll get z square minus z. Again, subtract. You'll get z minus 1. Plus 1 you do. So z minus 1. You can see that it's perfectly divided. It should divide because one of the roots was 1. Okay. So whatever you're getting, z square plus z plus 1. Okay. So one of the roots is this. So this quadratic equation, right, should give me the other 2 roots. Correct. We already know it's imaginary because we can't guess the real roots. Let's try to figure out. So what is z? So z is minus b plus or minus root of 4a b square minus 4ac by 2a. Correct. So what is minus b? So all the coefficient a is equal to b is equal to c is equal to 1 because in this equation, simple equation, it's x square plus x plus 1, similar to that, right? So minus 1 plus or minus root of 1 minus 1, 4 into 1 into 1, right? So it will be 1 minus 4 divided by what it is. So it is minus 1 plus or minus. Can you see the root is nothing but minus 3 now? Can I write it as root 3i? Because we have learned complex numbers, no issues. We know it's imaginary roots right now. So can you see now what are the roots? There are 3 roots. There are actual 3 roots right now. One is 1. The other one is minus 1 plus root 3i by 2. The other one is minus 1 minus root 3i by 2. Fine. So 3 roots, 1 minus 1 plus root 3i by 2 and minus 1 minus root 3i by 2. So we have a short form for this. What we do is we write 1 as 1 itself. This we write as omega and this we write as omega square. There's no particular rule. You can choose this as omega. The other one you can write as omega square. How can you interchange? Because if you multiply, can you check this? Let's see. Omega is minus 1 plus root 3i by 2. Let me just try to square it. That means I'm multiplying the same term again. Correct? The denominator is 4. Numerator is a plus b whole square. So it's 1. Root 3i whole square is minus 3. Correct? Then 2 into minus 1 into this. So it is minus 2 times root 3. What do you get? Minus 2 root 3i by 4. 2 is common. So it's -1 minus root 3i. Right? Can you see it's equal to this? So omega square. If you want to take the other one as omega, you will get omega square as -1 plus root 3i. Okay. So these are called cube roots of unity. So roots, it's clear. There are 3 roots, 1, omega and omega. But using these roots, there are a lot of things you can solve. Okay. To guess one of the properties is omega cube is equal to 1. Can you think of why this is true? Omega is a solution to this equation, correct? There are 3 solutions, 1, omega and omega square. Therefore, omega cube should be equal to 1. Okay, because it satisfies the equation. If you want, again, you can take omega, which is omega, this one, multiply it 3 times. So shall we try that? So it is -1 plus root 3i. This property will try. We have a different approach. We can do it in terms of angles as well. But we'll try here first. Minus plus root 3i into -1 plus root 3i by 2. Now, we have already multiplied these two. Therefore, I'll simply write the result -1 minus root 3i by 2. All I have to do is multiply this with -1 plus root 3i by 2. What do I get? Denominator is 4. Numerator is a plus b into a minus b. It's 1 minus root 3 square. Okay. So root 3i square will be -1. So it will be plus. Can you see it's equal to 1? Okay. So one important property we have already established. Omega cube, the cube roots of unity, omega cube is equal to 1. Now can you see what will happen? If I take omega, this is omega square. Now omega cube is 1. What would be omega power 4? Because omega cube is 1, this will be equal to omega. This will be equal to 1. Next will be omega power 5, so it will be equal to omega square. Omega power 6. Omega power 6 is nothing but omega cube whole square, so it should be equal to 1 again. Can you see the pattern will repeat? Right? So if I ask you what is omega power 2022, what will you do? We'll just divide the power by 3 and see what is the remainder. Okay. So here it completely divides. Completely divides, remainder is 0. If remainder is 0, what do you get? It's equal to 1. So all you have to do is just to figure out the powers, okay, you divide by 3. Okay. So if the remainder is 0, then your answer is 1. If the remainder is 1, your answer is omega. If the remainder is 2, answer is omega square. Simple. You can think, you can look at this. This remainder, which is 1, omega, omega power 4, omega power 7. Correct? You'll get omega square if the remainder is 2. Clear? If it's a perfect multiple of 3, the remainder is 0. Or in other words, it's equal to 1. One more important property you can think of. Because this is a root, it should satisfy this, right? So, one more important property is 1 plus omega square is also equal to 0. Because we know that, see, omega we got by solving the equation 1 plus z square is equal to 0. This was the quadratic which we solved, right? So omega also should satisfy this equation. Omega square also will satisfy. So omega square becomes omega power 4 is equal to 0. But we already know omega power 4 is nothing but omega itself. Sorry, omega power 4 is omega itself. But we have omega square here, so which I have written down here, right? So you still get 1 plus omega square equal to 0. This is also an important property. Why? Look at it. You can manipulate it any way you like. You can write what is 1 plus omega, it's minus omega square. You can even write what is omega plus omega square. It's nothing but a real number, -1. Got it? You look at some of the problems, how these properties are used, then you try to understand the importance of these properties. Now, omega is an imaginary cube root of unity. Okay. Then what is the sum? And directly, if you know the value of omega, simply substituting in the terms might get it complicated. Right? But we have all the important properties. So we know 1 plus omega square is nothing but 0. That means 1 plus omega is nothing but minus omega square. Can you see that? You can simply substitute that. It will be minus omega square whole power 7. So it is minus 2 omega square whole power 7. Or it is minus 2 whole power 7. Omega power 14. Correct. So omega power 14 is what? I divide 14 by 3. Remainder is 2. So still it's equal to omega square. So what is the final answer? Minus 2 power 7 omega square. If you want, you can write 2 power 7 as 128, right? Or you can leave it as it is. Okay, we have to try to find the summation. Okay. Now we have I and I powers. We have omega and omega powers. Okay. So let me try to figure out what are the terms. First I have 1, then I have omega, omega square, alternative terms. Okay. So if I write the alternative terms separately, 1 plus omega square, omega cube, so on. This will go up to 100 terms. Fine. The rest of the 100 terms should be I square, I cube, so on. So it will be I plus I square plus I cube plus I power 4. So this will be 100 terms. Then totally the terms will be 200. Just to know where it ends, the first one starts with omega power 0. Okay. So it will end with omega power 99. Totally 100 terms. This starts with I power 1. So it will end with I power 100. Fine. Now let's just try to simplify. Let me take this first equation here. This first equation is simplified. What is 1 plus omega square? We know it's 0. Next three terms, omega cube, omega power 4, omega power 5. What is omega cube? 1. What is omega power 4? Omega. Omega power 5, omega square. Again, this sum is same. Okay. Can you see we're going to get continuous zeros? We'll just see the last fact what it is. Omega power, say 97, omega power 98, omega power 9. We started with 1 omega square. We'll start with 1 here. Omega power 96 is 1. This would be omega, this would be omega. Again, this pair would be equal to 0. What remains is one single term, omega power 99, which is equal to. So we found the sum of the first 100 terms, okay, which we paired up. That is equal to 1. Now again, let us look at the summation of the below terms. Okay. Now I is I itself, I square minus 1, I cube minus I power 4 is 1. Can you see this is also equal to 0? So if I combine 4 of the terms, again I'm getting 0. Next 4 is 0. Because I power 5 is nothing but I power 6 is nothing but minus 1, I power 7 is nothing but minus I power 8 will be 1. So again, next 4 terms. What would be the last 4 terms? I power 97, I power 98, I power 99, I power 100. You can see we're using all the terms. So nothing remains. So the sum is equal to 0 itself. So what is the sum of all the 200 terms? It is equal to 1. Okay. If 1 omega and omega square are the cube roots of unity, then the value of these terms. Okay. Let's try to figure out the first one. 3 plus omega square. Okay, we don't have any relation, so we'll just simply try to multiply these two. For 1 plus omega and all, we know that is something different. Let's simply multiply. It's 9 plus b square is omega cube. Okay. It is 3 into omega plus 3 into omega square. Correct. Next term, if you want, you can multiply here 9 omega power 21 plus 3 omega power 10 plus 3 omega power 11. Clear? So omega cube is 1. So this will be 10 plus omega plus omega square. I told you this property is very important. Now you can see that omega plus omega square is nothing but minus 1. So it will be 3 into minus 1. Okay. Similarly, omega power 21 is 1. This is 3 into minus 1. Because omega power 10 is omega, this is omega square. Right. So what are we getting? 10 minus 3, 7. 10 minus 3 is 7. This is equal to 49. Yeah, all the complex numbers we multiply and what are real. Next. Second one. Same logic, I think. Okay. So we can see it is 3 power. Instead of positive, we have a negative signs now. So 9 plus omega cube minus 3 omega minus 3 omega square. The next term is a little different. It is 9 plus omega power 12 minus 3 omega power 4 minus 3 omega power 8. Again, omega power 4 is nothing but omega. This is omega square. Similarly, this is omega itself, omega square. This is 1, this is 1. So you can see that this is 10 minus. Now here we have already 3 into minus 1. Instead of plus, we got minus. So this is again 10 minus 3 into minus 1. So we have 13 into 13, 169 would be our answer. Just by changing the negative sign, right? So here we had plus, now we have minus. That's the only difference. Third one. Now, instead of multiplying, even if you multiply, you might get your answer, right? So instead of multiplying, we already have one more important result. Can you see this? 1 plus omega is nothing but minus omega square. Correct. 1 plus omega square is nothing but minus omega. Next term, let me see. Omega power 4 is nothing but omega. Omega power 8 is omega square. Same logic now. Minus omega square. Next is minus omega. Let me see the next term. 1 plus omega power 16 and 1 plus omega power 32. Right? Omega power 16, remainder is 1. So this is omega. Remainder is 2. So this is omega square. Again, we'll get the same thing, minus omega square minus. Okay, we are doing this for 2n plus 1 term. Remember, 2n plus 1 term, not 2n term. Okay. So let us look at what happens to these pairs. If I multiply these two, it's omega cube, which is equal to 1. So this product, entire product is equal to 1. This entire product is equal to 1. So each of this product is equal to 1. Great. But if you had even number of terms, okay, then I could have said the entire product is equal to 1. Now what do we have? Last term would be 1 plus omega 2n plus 1. Okay. It doesn't have a pair. Whatever pairs we had is over till now. So it's 1 into 1 into so on. All the product is 1. Now we have 1 plus this. Okay. So this is nothing but 1 plus omega square. Okay. You can keep it as it is or write it as minus omega. This would be a final sum. So we're going to look at nth root of unity. So now we're going to look at nth root of unity. So we have looked at z cube equal to 1. What are the roots? What are you getting? So in general, we look at what happens if you take z power n equal to 1. Okay. So you can guess. See, z power n equal to 1. Again, I can use a similar logic what I did here. Z cube minus 1 is equal to 0. So z power n minus 1 is equal to 0. Again, you can see that this is nothing but z minus 1 into z power n minus 1 plus z power n minus 2, so on up to. So you can see that one of the roots is 1. The other roots, similar to what we have done there, you can write it as omega, omega square, omega cube, up to omega power n minus 1. Got it? So one way to interpret what we are doing is, if you looked at the roots of a cubic equation here, right? What are we getting? We got 1 omega and omega square. If I write down what exactly we got, 1 minus 1 plus root 3 I by 2 and minus 1 minus root 3 I by 2. Two different values. So if you try to plot these points on the Argand plane, so just look at it. What is this? This is 1, correct? What happens? What is this point actually? If you try to write in terms of e power, okay, using the Euler's form, this is minus half. plus root 3 by 2i. So what is it? What gives me minus half? Cos 2 pi by 3. Okay. Other part would be I sin 2 pi by 3. Correct. This is nothing but e power I 2 pi by 3. Okay. And this will be e power I 4 pi by 3. If you want, you can check. It's a third quadrant where both are negative. Okay. So if I try to plot this point, just look at it. Okay. So this is Argand plane. Now we have this as your real axis, and this is your imaginary axis. So we are taking the magnitude to be 1. Correct. So where is 1? This is 1. This is 1 comma 0. So this would be a fine. What is e power I pi by 2? Same magnitude is 1. The angle is actually 2 pi by 3. That's it. So this will be somewhere here, say 130, 120 degrees. Next would be 240 degrees, somewhere here, say 60 degrees. Can you see what is happening? So your points, okay. So this is 120 degrees, and this is again everywhere it's 120 degrees, basically. Correct. So this is what you're getting. Okay. But can you see that? If I keep going like this, again root, if I again multiply, can you see the logic now? What we did? We did omega, right? So it was 1 here. So this was omega. When I multiplied the omega, I got here omega square. Again with multiplication, I got 1. Okay. This is how it was going back. Okay. Again with omega, that was coming because we were multiplying with the angle of 2 pi by 3. Okay. So 2 pi by 3. It was going to the next omega. Again it was going in a cyclic order. Right? Now can you imagine the same way? What will happen if I have z power 4 equal to 1? You can already guess what the solutions are. Okay? Z power 4 is not that complicated. Right? So z power 4 equal to 1 you will get when z is 1. What are the other possibilities? Z is I. Because we know I power 4 is 1. Even minus I. Even if it is minus 1. So you can clearly see solution. Otherwise, you could have solved it this way also. Z power 4 minus 1 is equal to 0. So it is z square minus 1 into z square plus 1 equal to 0. So two solutions here, you would have got your answer. So if you draw this, what do you get? Look at the points. Now our points, roots are 1. Again I. Length is only 1, it should be 1 itself. So this is say minus 1 and this is minus 1. When you see the root, we are rotating it by 90 degrees. Okay. So again, what will happen? The root, if it's 1 omega square, I'm just naming it as omega, okay? This omega cube without finding it if it's omega. Again, it will go in a cyclic order and this will be omega power 4 again. Clear? So by the same logic, what we are trying to do is any number of roots, right, we have. So this is the cube roots of unity. We write it in the same order. Clear? So what it will be? 1 omega square. So there are not much problems here, but whenever they say higher roots of unity, you should understand what we are talking about. So if we are talking about fifth root of unity, that means I'm talking about solutions of z power 5 equal to 1. That's all. So nth root of unity means the solutions of the equation z power n is equal to 1.